Now, our next speaker will be Dr. Sarah White, who's going to be talking to us about the GLEAM 4 Jansky sample. Hi, Sarah.
Thank you. Hi.
Hey, now Dr. Sarah
Is
White
it showing?
has some humble beginnings by studying at the University of Cambridge, where she sort of started falling in love with radio astronomy. And she followed this up with studies at the University of Oxford. And she decided the Northern Hemisphere wasn't really that cool, so she came down south to Australia to study to do her postdoc at ICRA in Perth. And now she's in South Africa using Meerkat, combining it with SALT, and also continuing with her collaborations in the low frequency back in Australia. Thank you, Sarah.
Thank you very much for the nice introduction, Moses. And thank you to the organisers for granting me time to talk about the GLEAM 4 Jansky sample. I'm a postdoctoral fellow, yes, at Rhodes University, based in the Meerkat office in Cape Town. And this sample is a compilation of nearly 2,000 of the brightest radio sources in the southern sky. And the vast majority of these sources are active galaxies. And by that, I'm talking about a type of galaxy where the gas and material is falling onto the supermassive black hole at the center. And as it does so, it produces a huge amount of emission over a wide wavelength range. And for the majority of the sources in this sample, we also have the production of these very powerful radio jets as illustrated here. Now, another phrase I'll use later in the talk is this idea of a radio core. And by that, I'm really talking about the radio emission that's connected to the accretion disk, so that whirlpool of gas, very close to the supermassive black hole at the center. So why are active galaxies important in galaxy evolution? Well, both black hole accretion and star formation are important processes that govern how galaxies evolve. And we note that they appear to follow a similar trajectory over cosmic time, both peaking at around redshift 2. Now, this suggests that there may be some feedback mechanisms that connects the two processes. But at the same time, it could also be down to there being a common reservoir of gas that fuels both the star formation and the black hole accretion. And similarly, there's debate over the overall impact of radio jets on their surroundings. So if we look at in the bottom left here, we have a radio jet impacting on an otherwise stable molecular cloud, triggering its collapse and subsequent star formation. But in other scenarios, you have that jet impacting on a cloud and completely dispersing the gas, and so preventing stars from forming. So that's another area of debate. And how does all of this tie in with the apparent co-evolution of the supermassive black hole with the host galaxy, as shown on the right-hand side? Now, remember that black hole is only a few milliparsecs across, and yet it's able to have an influence over kiloparsec scales. So these are the type of questions that we all know and love in galaxy evolution research. But then we have an amazing new instrument like Meerkat that comes along and opens a whole bunch of new questions. And as this image is shown already twice today by both Bernie and Rob, this is an amazing bright radio galaxy. So Empati produced this image using the Caracal pipeline. And thanks to Meerkat, its excellent sensitivity, but also good angular resolution, we can make out these never seen before collimated synchrotron threads. So we start asking questions like, well, how on earth did these form? How did they come to be? And if it was an issue of sensitivity and dynamic range that prevented us from seeing these before, then just how common are these threads across the wider radio galaxy population? So to answer those questions, and indeed many others, it would be worthwhile considering a complete sample of the brightest radio sources in the southern sky, also known as the GLEAM 4 Jansky sample. And it gets its name from each of these radio sources having a flux density above 4 Janskys as detected using the GLEAM survey. And this was a survey over the entire southern sky using the Murchison Wide Field Array, which is the low frequency precursor to the SKA in Australia. And here we have a histogram of the radio brightness for this whole sample. And we note that we're able to create a sample that's 10 times larger than the current most prominent low frequency source sample, which is known as 3CRR. Now, 3CRR contains 173 sources, but they're all restricted to the Northern Hemisphere. And if we want to investigate the properties of these radio galaxies as a function of redshift and as a function of environment, if we start chopping up that sample into those bins, we're going to be dealing with small number statistics, which isn't great for comparing to simulations. So this is why we need such a large sample, so 10 times larger than 3CR. Now, as mentioned before, the vast majority of the sample are active galaxies, but I wanted to just give a heads up to a few exceptions in the sample, and notably these two nearby starburst galaxies. So the combination of intense star formation giving rise to radio emission and these galaxies being so close by pushes their radio emission above that 4 Jansky limit. So not to just completely assume that 4 Jansky must mean radio jets. I wanted to spend a bit of time on these sources in particular because it was actually thanks to the beautiful, the displays in the beautiful SAO library that I learnt of their connections with Cape Town. So on the left, we have the Sculptor Galaxy, which was discovered by Caroline Herschel in 1783. And about 50 years later, it was her nephew, John Herschel, who observed this galaxy again at the Cape of Good Hope. And by that, they actually mean from the suburb of Claremont in Cape Town. And then on the right-hand side, another GLEAM 4 Jansky source is the Southern Pinwheel Galaxy, which was discovered by Lekai in 1752, also at the Cape of Good Hope, but by which they actually mean on the shore of Table Bay, just north of Cape Town CBD. So this Southern Pinwheel Galaxy also goes by the name of M83, but of course, it didn't acquire that name until Charles Messier had added it to his catalogue in 1781. Now, speaking of catalogues, for the GLEAM 4 Jansky catalogue, the two most important properties that we provide are a determination of the radio morphology, since these sources have very complex and interesting and weird shapes, and crucially, the location of that host galaxy that hosts the radio emission and allows us to cross-match on all the information we have from multiple data sets. In order to get to this stage, we had to start by feeding in a huge amount of information at multiple frequencies and wavelengths, and several passes of visual inspection to determine these. And this flowchart is basically a summary of all the detailed information that is provided in paper 1, which was published earlier this year. Now, to be absolutely certain that we have interpreted the morphologies correctly and indeed the host galaxy locations, there's also a number of literature checks that went into this work. And remember that literature checks are not automated, they're not pipelinable or anything. That's all manual work that's gone in to ensure high quality for this catalogue. And all of those literature checks makes a paper in its own right, which is paper 2, which is also published alongside paper 1. And I like to refer to it as the Hitchhiker's Guide to the Southern Radio Sky, just because of the variety of radio sources contained within the GLEAM 4 Jansky sample. Now note that for 14% of the sample, we don't actually have those host galaxy positions just yet. And that's because the current low frequency or images, and also even at higher frequencies, we have low resolution radio images. It's not completely clear what the morphology is. And if those radio sources are in particularly dense environments, then there are many host galaxies to choose from. So how do we know we've picked the right one? So these are the sources, 140 of them, that we followed up with Meerkat in the first open time call last year. And here are a few of examples of what we find. So on the left-hand side, we indeed have a bent tail radio galaxy. So those radio jets would have emanated from the supermassive black hole, but then due to the surrounding medium or relative motion to that medium, they become bent like so. And thanks to the resolution, we can also pick out the radio core, and so unambiguously identify the host galaxy for this source. In the middle, we have what's known as a head-tail radio galaxy. So here, the bending of those radio jets is so extreme that they're both falling in parallel in a southerly direction. And so we have good evidence that actually, yes, the core, where the supermassive black hole is towards the north. And then on the right-hand side, even with the higher resolution image from Meerkat, it's still not clear what the morphology is. And so this is where we would want to obtain further higher resolution images and also calculate a spectral index map to hopefully locate the flat spectral emission that's associated with the radio core. Now, if you were to have 10 hours on Meerkat and wanted to observe a particularly extended GLEAM-4-Jansky source, then you'd be able to create an exquisite image such as this. So this has also been shown by Rob and Bernie earlier. And the idea here is that we have this beautiful morphology because the radio jet is switched on in an almost northerly south direction. It's energized the surrounding medium, creating this plasma that then falls back towards the center because it is still part of this potential well. As it falls towards the center, it then encounters this dense reservoir of gas that is causing a deflection, and that less dense plasma then follows the path of least resistance, taking on this very nice kind of boomerang shape. And if you look carefully within the lobes, you see this lovely filamentary structure as it's kind of curved round this bend close to the center. And so all of this is observational evidence and argues for the hydrodynamic explanation for these X-shaped sources. Because the other explanations were that, well, one, maybe the radio jet switched on in the north-south direction, switched off again, reoriented itself due to some perturbation, and then switched back on, creating the east-west axis. And the third explanation would have been that, or maybe if there are two supermassive black holes that are orbiting one another, then each of them produces their own set of radio jets, which are then superimposed. So all of this beautiful work with Meerkat is arguing for actually the hydrodynamic case, this backflow scenario. What's also really nice, because of the excellent sensitivity of Meerkat, we can pick up this very faint emission, this cocoon surrounding the lobes, which allows us to actually probe the pressure of the intergalactic medium, which is very cool. And on the left is just a shout out to other projects that's been conducted using Meerkat, and that also overlap with the GLEAM-4-Jansky sample. So do keep a lookout for that work too. And coming on to my final slide, in the top left, we have a comparison of spectral indices. Now, it's often assumed that the radio emission is just simple synchrotron emission and follows a power law function. But if that was the case, then all of the sources should lie along this dashed line shown here. So the fact that we have this degree, this spread of the data points around that line gives you a feel for just how much spectral curvature there is in the radio part of the spectrum. And that's an example of that curved spectrum is shown on the right-hand side. So at low frequencies, we're actually picking up the cumulative effect of AGN activity. And that's because as radio emission ages, it moves to lower frequencies. And this is one of the reasons why we do our selection at low frequencies there. Whereas at higher frequencies, we're really probing more recent or ongoing AGN activity. And to just draw a parallel with star formation, at the longer wavelengths, like in the near infrared, you're probing the old stellar population, whereas the shorter wavelengths in the blue part of the optical, you're really probing more recent ongoing star formation. So this, by sampling the full radio frequency range, we can get a better handle of the life cycles of these active galaxies. And this is a nice demonstration of how the two components of the SKA in Australia and South Africa will complement one another in the study of active galaxies. Now note that all of the analysis done so far is limited to the observed frame, and that's because we don't have good spectroscopic coverage over the Southern Hemisphere. And this is why we've started this multi-semester campaign using the Southern African Large Telescope. And I'm also happy to say we have follow-up data using the Australia Telescope Compact Array, which is what gives us these really high frequency data points at 5, 8, and 20 gigahertz. And we're looking to observe more sources with Meerkat, of course. Now, please do check out papers 1 and 2, which were published finally this year. It's a culmination of 4 years of work. Thank you very much for your attention.
Great. Thank you very much for that lovely talk, Sarah. Very, very interesting work. Yeah. And thank you for those of you who have already submitted some questions, and feel free to add some more to the list. First question that comes to us today is, do you think the AGN synchrotron threads are analogous to those seen in the galactic center image?
Well, it's all, the usual answer would be it comes down to magnetic fields. So the thing is that the threads look as though they've been formed in a different way to the very nice filamentary structures you see in the galactic center image. So that the more recent paper by Ian Hayward, which was about the bubbles emanating from the galactic center, you can imagine those bubbles are then compressing around their surrounding medium, creating these kind of shock fronts. And it's crucial that we have that kind of compression if we're going to accelerate electrons and produce the radio emission. So the mechanism is actually slightly different. What's super weird with those collimated synchrotron threads is just how well they maintain their structure over a large area. So they were 1 kiloparsecs wide, and one of them was, I think, 80 kiloparsecs from end to end. So how they maintain that is also, we don't know yet.
Right, we've got a question here from Kevin. Do you have any thoughts on AGN as progenitors of fast radio bursts?
Oh, gosh. Interesting question. Locating the hosts of fast radio bursts is obviously an area of a lot of research. And I personally don't have an opinion yet, because there seems to be like one paper saying this and one paper saying that. Maybe it's detected connected to a dwarf galaxy, which is less likely maybe to be hosting an active galactic nucleus. And then you have also connections to maybe maser systems. So I'm sorry, I can't really, it's maybe a bit beyond my expertise, sorry.
Right, thank you very much.